Okay, so good afternoon. I am proud to have the last talk of the conference, which is a nice spot to be in. Okay, so I've been in research for a while now, 8 years in the research lab, and I've noticed recently that PL is no longer the hot topic anymore. The hot topic today is ML, right? Machine learning, not the language. So how are we going to fight the machines? Because the machines are eventually going to take over. They're eventually going to win. Make no doubt about it. I mean, we're done for. But hopefully that's like 50 years from now. But until then, we have to, fight this battle between PL and ML. And we have to, in order for us to do that, we're going to have to become cyborgs, right? We're going to have to use the computers more efficiently in writing code. No longer can we just use Emacs and dynamically typed languages and compilers and do everything in our head because the competition is getting smarter. So we're going to have to also get smarter. So I titled this talk "The Mother of All PL Demos," but it was more of an aspirational thing. I don't think I'm actually going to get there. But I'm sure you guys will all still be entertained. Brett Victor, back in 2011, he really did a mother of all PL demos, right? I don't know, is anybody familiar with Brett Victor's work? Ah, good. So maybe you'll think a lot of my stuff is original. That's great. Some of my stuff actually is original, but a lot of it, he was a very smart guy. He showed a lot of really wonderful concepts, and I copied a lot from him. And in the sort of tradition, I'm trying to do my own, get together my own like grand PL demo so we can sort of push things forward. So programming, I posit that programming benefits greatly from increasingly better feedback loops. So if anybody around here was programming in the 50s, and I don't maybe think anybody is, but oh man, there's two screens here. Right, so there's these ladies with the switches, right, trying to, program the computer, right? And of course, we then stepped up a little bit. We got card punches and then teletypes and wonderful. And today we have, keyboards and we have multiple monitor displays and we can actually compile our programs at our terminals. And, we even have IDEs that give us syntactic or compile time feedback right away. So we have we're getting better, more tighter feedback loops compared to what we had, in the 50s, in the 60s, in the 70s. What about tomorrow? What will programming look like tomorrow? And if anybody says slightly better than what we have today, that's not interesting, right? This is what we want. We want, what we see in the movies, right? If you're going to build your power suit to fly around and fight, bad guys, you need a next generation programming environment, okay? And this is all fictional. These are all fictional interfaces, but there's an element of reality to them, that the experiences will be more and more fluid. That's what we want, and that's what we should be aiming for. But what does a more fluid experience mean? So, there's this term called live programming. And I'd like to say that it was, at least the view I subscribe to was invented by this researcher called Chris Hancock. He did this dissertation in 2003. It was beautiful, big ideas in computational literacy and real-time programming. And what he stated in his dissertation was something called this water hose, right? We want programming to be like a water hose. And what does that mean? So think about archery. You shoot the arrow. You aim, you shoot the arrow flies, and maybe it misses the target, and then you have to shoot again, right? But that's a really horrible feedback loop because each time you're kind of starting over again. Maybe you're really skilled and you can kind of steady your aim well enough so that you can actually not start over again. But most of the time it really is, for most of us, right, it's like really hard. And there's an Olympic sport for archery because it's a very hard thing to do. Now, compare that with hitting a target with a water hose, right? This is easy. You take the water hose, you move the water hose over, and you hit the target, and it's done. Very easy. And why is that? Because you never stop aiming. You just move it until you hit it, and you're done, right? Whereas the archery stuff, you stop aiming, and you start aiming again, and you have this disconnected user experience. or programming experience. Well, if we say it's programming, then this is programming today. You write your code, you hit compile, you test it, and then you see where it fails and you start it again, right? That's archery. We're at the archery level right now. We really want to be at the water hose level. So I'm going to break into a demo here. Most of this talk is going to be demo, but I added some slides because give you guys some more context, right? And so the first sort of feature I want to that I'll show is sort of this idea that language design shouldn't just focus on expressiveness, shouldn't just focus on the language. It should focus on the programming experience, the execution, the IDE. And one way I've sort of manifested this principle, right, is in these holy terms, right? And what's nice about these things is that, the language has a way of expressing things that you don't know what they should be yet. Then you can do co-completion, or then you can even execute those. It'll make more sense when I actually do the demo, but I just wanted to give you a little bit of context before I did that. Right? And then scrubbing. So this is where we get back to the water hose. So who here kind of knows what a continuous function is? Yeah, okay, cool. What's really cool about a continuous function is that you make a little change in the input and you get a little change in the output, right? And what we really want is continuous functions for our programming experience. We want little changes in the code will result in little changes in the code the execution output. And then we can just sort of like, okay, go up, down, okay, better, better, worse, 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 right? Because that's what continuous functions give us. Right, and we can manifest this in something we call scrubbing, and I'll demonstrate that really quickly. Here, and then there's just seeing things, being able to see things in your programming execution, right? You want to see how the program executes without actually running the program. Maybe you have a strobing effect where you can see a ball, in multiple frames, or you can see the data without actually having to, print it out explicitly, or you can just see it as it changes. Okay, so with that in mind, I'm going to do my first demo. Let's see if I can remember which one it was. No, not that one. Here we go. Okay, so now I'm in my programming environment. I'm going to type a question. Right, this is a holy term. Can you guys all see that? I don't know, these are a little bit smaller than the other place. Okay, well, it's just a question mark too. There it is, a question mark. Okay. It means I don't know what I want to put here yet, right? I didn't know exactly what I wanted to type. And this provides an excellent sort of context for co-completion. So we're going to do co-completion here. And we have a few methods, not a lot, because it's a prototype. But we have one thing called draw. I'm going to select draw. And as soon as I selected draw, right, a little square appeared on the screen. I don't know if you guys can see that here. This square appeared on the screen because, it's executing, right? But what happens is when I selected draw, all these other holy terms appeared. One for the receiver of the draw, one for the color, one for, I don't remember what that is. Oh, the pen, right? And then the z-index, okay. But one for the color here, right? And if I can do co-completion on this, then we can have a blue here. And I can do co-completion on this guy, and hey, we can have a circle, okay? And then we have more holy terms. This is the position of the circle, this is the radius, and this is, or the diameter, or something. And this is the rotation, which doesn't make sense for a circle, but anyways. Right, so then I can go ahead and turn this into a tuple. We can put some numbers in there. We can put some numbers in here, right? And this is you might have seen demos before where people are writing their JavaScript code and it's re-executing in real time. Right? So that's cool. I mean, when the first time you see it, they say, yeah, that's cool. Then the second time you see it, it's like, yeah, maybe that isn't so cool. Because look what happens here. Like, let's say if I want to change this 100 to 200, right? I have to delete the 1, hit the 2. Delete the 1, hit the 2. Everything's kind of just jumping around. It's not really smooth. It's not fluid, right? And so this automatic re-execution thing isn't very useful. Well, it's useful, but it's not as useful as it could be because we don't have a very fluid programming experience. So what we can do is we can scrub, right? And scrubbing basically means I'm going to use my mouse, and this is actually where the mouse is actually useful in programming, right? I'm going to use my mouse, and I'm going to just change the constant, by scrubbing the value, right? So we can scrub this back to 100, maybe 150. We can scrub this one, The idea here is that now, instead of just having things jump around on the screen, they're moving very smoothly, right? And so now we can actually put it where we want it to put it. We can even scrub both of them at the same time, right? Move it around like this. We can do the same thing with the radius. But we can also do the same thing with the color. And the color is not something that you generally think of as being scrubbable, but, hey, we have blue. We have a list of other colors that are, literal colors, and we just scrub between them. And as we move the mouse through the list, we actually see the color that we're choosing, right? It actually executes, right? So we make that red. Or maybe we want a tuple color. Or maybe we want something else, more precise. Maybe we want to deal with the color coordinates, right? So then we can scrub those. And we can also scrub these individually afterwards, I hope. Yeah. Okay? So, so having this ability to scrub things works really well in this live programming context. And actually, before I was just doing, type your code and see the execution on the screen, and that was not good enough. And now I actually feel like, wow, this really is better. Okay, so I'm going to go and do a more intense example, but I need my little rectangle there first. Okay, good. So let's go ahead, and I have some code set up here. Okay, so now we have a circle. We're drawing a circle on the screen. I have a lot of other stuff there, some utility functions and things like that. And we're just going to make this circle move, right? And to do that, first we need to have it positioned in the center. We need a position in the center of the circle, because if you do any physics computations, it's really hard to do it from the left-right corner of the circle. So we do this position here, and we do D, and then we subtract that. We subtract this, and we divide it by 2. So this is the radius times 2, and we divide it by 2, and we get sort of the dimension. We get the position circle. So if we do that here, and let's say we give this a position, and let's say we give this 75. Right? As I scrub this, you can see now the position is being scrubbed from the center of the circle versus the left top corner of the circle. Okay. So now we're going to make the thing move, and we're going to say P equals P plus V divided by 50. All right. So now the circle is moving. Okay, it's not really moving. So I have this on tick here. I think that's an event handler that goes off every tick of every frame, basically every 15 milliseconds, right? And we have 200 ticks that are preloaded in our system. And what that means is that we just go ahead and we execute the program for 200 ticks, and we strobe on every 20 ticks to provide a rendering of where the ball is going. So if we scrub tick here, right, we can actually see the ball move, right? This is just saying, this is time 0, this is time 167, okay? And we can also play with this, the velocity, to sort of, to see where it would go. And the velocity is pretty boring, so we should add, force. Okay, now we have a parabolic trajectory for the ball. And again, we can scrub it. We can see the ball kind of fall off the screen. We can change the force. This is probably what they meant by use the force. Okay, never mind. Right? Yeah, I can, move it like that, and we can make that negative, and it gets kind of cool. All right, let's just not make that negative, though. All right, and make that 0. Okay, so now I want to make the ball bounce. So I need to do a couple of things there. I need to, I need to do this first, actually. Oh, hopefully I don't cause a crash because I went off script. I need this expression below here, this dd divided by 2. So what I'm going to do is I'm going to create a new value, rr, and I'm going to give it the holy term, because the holy term is something that I don't know or I don't want to type again. And I'm going to take my mouse, I'm going to click on the holy term, and I'm going to ground it on this divide symbol, and that will just move it up. So this gets the expression, and the value moves down here. Okay, so it's like kind of like micro refactoring in the language. And these holy terms are incredibly flexible for that kind of thing. Right, and again, I do the same thing here. I have this P1, and I'm just going to, use the holy term, move all the stuff up and have P1 take its place. And then I'm going to clamp it because, you don't want things going off the screen. It's completely not cool. So RR was like the minimum, that's like the minimum size of the ball, and we can use screen size here for the maximum size. Well, that's not quite right. I need to subtract RR from screen size. Okay, now that's good. Okay, so now the ball at least is not going off the screen. All right, and we need to do something else. I wrote these utility functions before the talk, so we have this inflect here, which will look at the position, and if it goes off screen, it will inflect the velocity. We just have to do a pairwise multiplication of the vector. So when I do that via times, inflect, and we need the position, P1, and the RR, I guess, minimum. Okay, now it bounces. Okay. So now we have a bouncing ball, which is like hello world or writing a compiler in the PL as a validating example for live programming, because you always see it. And now I'm going to take this and I'm going to wrap it up into a procedure. This is the one that crashed in the last talk. Hopefully it doesn't crash this time. All right, so I'm just going to do the same thing. I define a new method, I give it a holy term, and I'm just going to drag it. And it should just disappear because the method is no longer being called. I'm going to go up here and I'm going to type a loop for I in 0 until, let's say, 10, and colon, ball. All right, we're only seeing one ball and there's 10 iterations, but the problem is I gave them all the same position. So I'm going to turn this back into a holy term, Control K. Right, now they all have unique random positions. And the holy term is really cool because what it does is it computes a value if you don't specify a value, right? And it provides a unique value so that not all your unknown things don't appear in one place, which is really useful. And like the colors too, right? I mean, these guys all have different colors, even though I didn't assign them colors. I could make them all blue, right? But then they're all blue, and that's not useful. So it really is just nice to have something that just gives random colors to everything, right? So now we have a lot of bouncing balls on the screen. We can kind of see how they move. We can, change them in mass. Okay, now, let's see, what was I going to do next? Oh yeah, and we can also scrub the loop here, right? That's like 5. Let me do some return here so we have more space to see what's going on. Right, 0, 1, 2, 3, 4, 5, 6, 7, 32, 33. Okay, let's go back to something reasonable like 5. Okay? Then we have 5 bouncing balls, and we can scrub that just like we can scrub everything else. Right, and we can also see things. We can also inspect the values here. We can do I have to go up here, and if I do a Control G, then it will go to the method. This is like go to definition, but it's like go to definitions, go to execution also. And now I can do things like probe the color, right? And I can also type a little @ symbol here that will just show it on the screen continuously. And this is actually kind of cool because now you've pinned some probed value there. You can see it forever. We can do that for position too, right? If we scrub this, right, we can see it's moving, and we can see the position is changing in the UI, right? And well, we know what kind of ball it is. We know this ball has the same color as this, so we know it's this ball right here, right? And we can change this, right? We can scrub the loop iterator, right? Now it's the green ball, now it's the purple ball, black, and whatever that color is, right? So we can totally navigate through the entire execution of our program. We can also do this thing called log. All right? And in this case, right, now we get position and velocity, right, for each of the iteration. Oops, that was not a good idea. That's okay, we recovered. I'm running out of space. All right. Right, we can see the velocities and positions here. And there's a two-way connection here, right? We can actually click on this, and we're at the first one, we're at the second one, we're at the third one. What this does is when we click on a log entry, it goes to the log statement, as you would expect. Well, not really, but you should expect, right? But it also goes to the execution context of the log entry. So it's useful for debugging, okay? And we can actually look at one of these guys here. Let's look at this one here. When it bounces on the wall. No, that was too much. All right, there you go. And then we can look at the value here. One of these is -1, -1 and +1. The x is -1, so if we go to Control G there, we jump down into the implementation of that, and we can see the values there. That's -1. That's causing it to bounce off the wall, this dark purple one. And that's not bouncing. We go do that, and we can see why this value is, its x value is 681.79, and the maximum is 681.5. That causes the -1. That causes it to bounce. Okay? So you can see things. You can see a lot of things. And you're not setting a breakpoint here. You never set a breakpoint. It's all spatial, right? I'm just scrubbing around my loop iterations and adding symbols and hitting log entries, and I can see all the values in my program without ever typing in a breakpoint. Okay, so let's go back to the slides. All right, so I have another demo here. So this is my first demo, so we're going to do another 2 demos. And what I showed you before, okay, scrubbing and this holy term stuff. And so now I'm going to show you some other stuff on abstracting. So people do not deal well with abstraction. It's hard, right? And there's other ways of doing abstraction, right? Instead of just saying, think really hard about the problem and then type the magical abstractions into the computer, and then you'll get the right concrete representation for each instance of that problem, right? But there's also this way of starting with a concrete example and then abstracting that. So we're going to do that. I'm going to show you an example of create by abstracting, right? And then I have this like inside-out picture where everybody goes crazy because the abstractions are just weird. And also sketching abstractions, right? So what we're going to do is I'm going to show you an example where we're going to sketch things on the screen and they're going to be abstracted aggressively. So two more demos to go. Let's go this one. Let's just nuke everything on the screen. Make sure the tick is 0. Good. All right, empty. All right, that code is all gone. I'm not seeing my cursor anywhere, so why don't I go ahead and restart this. All right, well, it's just as good as empty. All right, so what I'm going to do now is I'm going to hit the screen 3 times. And each time I hit the screen, a shape is going to be created. So this is for the demo, right? So I can hit the screen here once, and there's a rectangle where I tap the screen. Okay, I'm going to scrub that into a circle. I'm going to move it to the corner of the screen and resize it. Okay, now I'm going to do that again. And this one I'm going to leave as a rectangle. And resize it to a particular shape, 150 here. Okay, I'm going to build a pill shape here, so we need one more shape, set to a circle, and moving it into the position here. Say 150 and then 100. Okay, so notice that now before I was actually scrubbing in the code view, and now I'm actually just manipulating the shapes directly. It seems like a reasonable way to manipulate shapes by moving them directly. And now, I'm resizing them with this dot, and I'm moving them with this some dot up here that we can't see anymore. There, okay? And now if we tap this, right, we're going to now do a union. So all I have to do is select this shape, and then control-click on this shape, and we do a union, and control-click on this shape, and we do a union. Now we have a pill sort of shape thing. And now we want to make the size parameterized. Okay, because we have this pill, but it's like 100, 150, and we really want something that's a lot more flexible than that. So what we're going to do is we're going to create another value here, a holy term. And we're going to say, well, there's a lot of 50s, 100s, and 150s repeated here. So maybe we should turn those all into the same variable. So we're going to take this, this holy term, we're going to drag it on this tuple. Right? And it just, again, it swaps out the concrete value for the value I'm defining up there. And then we can take this 150, we can drag it onto that. We can take this 100, drag it here. And there's another 100 over here. This one is kind of weird. It's 50, so we'll just say, well, maybe it's related to 100. So what we do is when we drag it, we get the arithmetic expression, right? And OK, maybe that's right. So let's make it bigger. OK, that seems fine. Let's keep it at around 200. OK, 199. The problem with scrubbing is that it's not very precise. All right, fine. OK, and then, but if when we do this, ooh, that's not right. We've kind of miscalculated the height. Right? So for some reason, this expression is wrong, but it could be something else. All it has to do is be some kind of expression that, don't do that, involves sd0.sy and computes to fit to 100. So let's look at what the other options are by scrubbing that. So we have minus 50 times 0.5 and divided by 2. Right? They're about the same thing, right? So we'll select that one, right? And now that also takes 100 divided by 2 is, right? 100 divided by 2 is 50, right? And 100 minus 50 is 50. So they're equivalent for that use case, right? But there are different, depending on what abstraction you choose, has different effect when you change the height. And now it works. So we've done a creation by abstraction here. Okay, and then we just need to turn this into a method. So let's create a position here, 100 by 100, and translate by P, right? And let's go ahead and define a method here. Def pill, return question. So we're going to do the holy term thing again. Now we're going to do it for something that has a return value, which is a little bit more convenient, right? So what happens is that now we've refactored this into a method, and it's replaced it with a call to that method. And so everything in the program stays the same. We're just abstracting it more, okay? And we can even do things like this. We can take this position here, and we can scrub that, right? We have other options. We have val, var, and arg. We want to make it an argument, right? We want to make a parametric method, right? So we make it an argument. What happens then is that an argument is added. We take the concrete value that p used to be, move it to the call, and everything stays the same. We can do the same thing with this. This is technically not correct, but we'll just do it for time. Right? Now, I can move this here and change the size. Technically, it's a bit weird because the size isn't exactly right. Okay. So let's add some rotation here. Val r, it's like 13 degrees, and then we can do just rotate r. Right? And then we just change this into an argument like before. So now we have a shape that has a position, a size, and a rotation. And if you remember before, I had rotation in all my shapes, right? So when we scrub, we draw a shape. We choose one here. But when we scrub this now, pill has the right template. It can be a shape just like a hexagon, a pentagon, a triangle, whatever. We can actually then add that to our scrub list, and we can access it via scrubbing. Okay? So we can just, build up our shapes and use our abstractions. Okay? So now I'm going to take a different tact. So I'm going to get out of this program. I'm just going to close it down. And I have another program. So this one, okay. So I show these demos, okay, people like them, right? And I show my lab manager, and he says, yeah, this is cool, but how does this help Microsoft? I work for Microsoft, by the way, right? And so, yeah, it will help Microsoft in 20 years. He said, that's not good enough, right? Got to do something for Microsoft today. And we have all these wonderful Surface devices like Surface Pro 3 and Surface Pro 4 and Surface Book, right? These are awesome, right? Because they have little pens. You can use them for sketching. And that means you can use OneNote with them. But maybe we could use them for programming. Maybe we could use the pen for programming. Because we've already found that the mouse works well for programming given the right context. Maybe the pen would also be good for programming. Okay? So what I did was I got together with my HCI colleague. Okay, we're working on a new thing that is basically about, we're going to sketch layouts. Okay? So I'm going to sketch a layout here. Right? So I have my I don't have a pen on this machine because it's not a Surface. It's I don't know what brand that is. It's an Apple something. But you can imagine that this is designed for stylus, right? So I'm going to sketch a square or a rectangle here, and what's nice when you sketch something, you can say, okay, well that looks kind of like a square, but then of course you take the ink and it doesn't look anything like a square. It's like really crooked and everything, but you can smooth that out. You can say, well, we're going to recognize this as a square, right? And that's a very simple, very common thing that happens, right? And then we're just going to replace the ink with a square. We're going to dry the ink as a square, basically, is what they say, right? And now, let's go ahead and let's do another one right next to it. And you can see my sketching with the mouse is really bad. But my sketching with the mouse is really bad, but this is the exact same rectangle, square, right? And it's not because I was really precise and I was able to draw the same square twice. It was because, well, that square was adjacent to that square, right? And let's say, well, since you're not being precise anyways, let's try to match what you did previously. Let's look at the adjacent shape and let's share variables. And when you share variables, something magical happens, right? You just don't have two rectangles anymore. You have a program, or well, at least a parameterized drawing. Right? So if I select this one here, and if I make it bigger, right, or if I change the location, and I make it wider, they both are affected because they're sharing variables. And I can show you the code over here. This is simple procedural code with a special syntax for declaring values, and that's it. There's no constraint solving going on here. This is just normal code. Okay? So now, we can do two more. Hello. Okay, and so we had two more. They're all the same, because I drew them about the same, and the gaps are even copied so that the gaps stay constant, right? And what we get is all these red lines here. If I want to disconnect this thing here, I can click on this guy, right, and we can see the red lines. And I don't know if you're familiar with design, but these red lines are sort of ways that you sort of describe your layouts, right? And we have two red lines here. We can disconnect this, I hope. Let's see what happens when I do it. Right, and now it's no longer bound, but then I can reconnect it over here, and it will be bound again. Right, so we have this way of programming without writing any code, and this is something that designers should be able to use, hopefully, on their Surface Books that they bought from Microsoft, and maybe. And I can draw a shape over here, and of course it's completely unrelated to this shape. But as I move it in, you see the red lines are popping up. They're becoming active. Right, over here, you see some red lines here. We can align it there. We can align it there. Let's align it like that, right? And then I can move it over here, and you can see we can align it on this edge too, right? And then if we do that, we can see, oh, we don't see anything else. Oh yeah, we see that one. This one's good, right? So now I'm taking this shape in, I'm putting it in post priori. I didn't draw it next to it, but it doesn't matter because I can just move it close in. And you see the guidelines in PowerPoint. They say, oh, this is a good alignment. Why don't you stop your shape here if you want, right? I don't know if you guys use I mean, all the drawing apps are like that. But this is different. This is saying not just, why don't you align them for this instance? Why don't you align them forever? Right? And so now you know, and now that this is aligned forever, if I move this guy down, right, that shape moves with it. It gets bigger. And if this shape gets wider, it all gets wider and it gets smaller. Well, that one's not. Well, I can fix that right away, actually. Click. Right, now they're all bound. So the idea here is that, you know, people can sketch parameterized layouts, or programs, as programmers would call them, without ever touching a single line of code. All right, and I got one more example here, so I'm just going to restart this demo because I don't know. So one more example here is, okay, you know, geometry. People love geometry, right? It's kind of easy. That's not easy. It's hard, right? So I'm going to do we're going to do a shape here, and we're going to use programming, but we're not going to touch any code. Okay, I'm going to draw a line, and I'm going to draw another line. So I got two lines here, and I'm going to draw a perpendicular from this line, right? So I'm just going to draw a perpendicular, right? And what happens is that I didn't draw an exact perpendicular. It just aggressively abstracted. It's kind of perpendicular, and it's kind of in the middle of the line, right? So we're just going to take that, and we're going to fuzzily add a perpendicular line that's exactly in the middle of the line, right? And another thing is, you know, we have these two. Oh, I didn't mean to do that. Undo. Right. And now we have these lines are intersecting, right? So intersection is also one of those things that they have actually a mathematical formula for it. So I'm going to draw, I'm going to draw a line to that intersection. Okay? And if you look at the code here, we have the perpendicular code here, and we have the intersect code here, right? And this is all, I just drew this, and it's all parameterized. Now, if I start playing around with these things, right, you can see that as the intersection point of those two lines changes, so does where that line ends that I just drew. And if I do this, right, you know, you can see the perpendicular is changing, the intersection is changing. We can manipulate from this point. We've just created a solution to a geometry problem without doing any geometry, right? We can even sort of change the, you know, where this perpendicular line comes out. Okay, so there's two things, right? One is layout sketching, but then there's also this ability to do trigonometry and geometry without actually doing anything, you know, just saying, oh, I kind of want this, right? And, you know, and then, you know, we know how to reverse engineer and say, oh, well, these are the right abstractions to do that, right? Which allows, you know, programmers to do a lot more things than they were able to do before. That's it. That's the end of my demos. So let's just go back to the slides, and I have a few wrap-up slides here, right? So I want to revisit the water hose that I introduced in the first demo, this scrubbing, right? Little code changes, little output changes. That means you can sort of and you can sort of tweak your program until it's right. The problem with that, it doesn't apply generally, right? It applies to constants, it applies to positions, it even applies to simple abstractions like color and shape. But it doesn't apply to, you know, loops, conditionals, and everything else that you might do in a program. So there's a lot of future work here is to make scrubbing useful so that we can actually scrub, you know, we can use scrubbing a lot in our program so that we can actually take advantage of this auto re-execution while we're programming, right? One idea is to scrub two concrete values and then scrub abstract values and go between the two. And this is kind of like what machine learning does, but well, yeah, we're all going to become human machine learners pretty soon. Okay, and I just want to mention a couple of the technologies behind this work. Right, one is the virtual time machine. So I mean, you know, all this live programming stuff doesn't come very easily, right? You need a lot of technology behind it. So how many people here are using React? Because you would be in the other talk right now, probably. I guess not many. Okay, good. Or one. Okay, so React is this great thing. It takes your retained model, retained UI model, and provides it with an immediate mode veneer, right? And that's basically what we want for live programming. We want to have this idea where, if any kind of change is done, we want it to be actually incrementally reincorporated into the program execution. Just like, React reincorporates changes into the virtual DOM, right? And this basically means that whenever there's a change, for example, if we want to move the position here, right, and we change it down here, this change gets propagated up, because this position has changed, and so the circle moves, right? And if we actually change the code, then that just means that when the code is in a decent state again, that change is propagated immediately into the program execution. And writing a system like this is, I don't know if you're familiar with those like little segues that you just kind of stand on and they self-balance, right? Continuously you're unstable, right? We did not make it stable by default. If you want to make that stable, you would have added training wheels, right? Wheels in the front, wheels in the back, then you would never fall over. But that's no fun, right? So they add a gyroscope in there. So they say, we're going to make you continuously unstable, and we're going to make you stable on each, at each moment in time instead of making the system stable to begin with. So that's the technology that kind of underpins this. And the other one is this typeless type system, right? This is all the code I showed you in this talk was statically typed. And there were no type annotations. And the way we got that was by inferring types based on how terms were used versus their definitions. Because traditionally you say, oh, the value was defined that way, so we can give you a type. But that doesn't handle things like holy terms very well, right? The holy term could be anything, right? It depends on how it's used, right? It gives it a type, and that type gives it a default value, and that default value is red. Okay, and one of my friends kind of called this quantum typing, right? It's typing based on observations based on how the value is used. Okay, so I'm at the end. So I just want to leave you here with something that, so when Brett Victor gave his sort of talk at Strange Loop in, I think, 2012, right, somebody asked in the audience, this work is great if you are creating art and processing. What about when I'm writing a compiler? What should my editor do then? And Brett said something really prolific there. He said that these are design requirements for a good environment. How do we change programming to fit? So what we're working on right now is we're trying to come up with a list of good things that we want in our programming environments. And they're not going to exactly fit our current practices. But the long term is we're going to try to make them fit, right? So that we can actually get that Iron Man experience that I showed you before. And that's it. I can take questions now.